All right, welcome back, everyone. You are in the application track, so I hope you're in the right place. The next talk features Director of Disruptive Technologies from Elsevier Labs. Please give a warm welcome for Sujit.
Thank you, John, and thank you all for coming. It's a pleasure to be here, and I hope you enjoy the talk. Right? So, a little bit of introduction before we start. I work at Elsevier Labs. My interests are search, natural language processing, and distributed processing. The group I worked with, we have a website. It's labs.elsevier.com. You can contact me at the email address and the Twitter handle. A little bit about Elsevier. We are the world's leading provider of scientific and medical information. We have a lot of data science practices going on because we work with the user to provide data and information systems. And like everybody else, we are hiring. Little bit of agenda before we start off. I'm breaking it up into 4 parts: the overview and background, basically saying why we did what we did. Another little bit of talk about the feature and the features in the API. Then we talk about the scaling out piece. And finally, we go to the Q&A. So initially, I mean, the reason we embarked upon this whole dictionary-based annotation is because we have a pipeline. We are building one. The pipeline consists of reading documents, a very large number of documents as our input, and creating a knowledge graph on our output. So you can, it's clearly that you need to have a way of finding entities in the text that you are reading, right? So that's where this comes in. We did consider looking at statistical NERs, but unfortunately the ones that get trained on a very small subset of things, right? People, places, organizations. Because our domains, we have so many domains, right? So math is different from biology, is different from medicine, right? So, and each of them have their own unique vocabularies. So for us, it was a better idea was to take advantage of linked data that people have already built in different disciplines. And so what we do is we take the linked data, we create a dictionary out of it, and then we send text through it, right? While this is a simplistic approach, obviously, but it's not simple when it's done at scale, right? So one of our corpuses, one of them is ScienceDirect, and that has 14 million documents. Scopus has 60 million documents, and so forth. Apart from this, we also have dependency parsing inputs, like triples. So we need to also do those. Just to give you an idea of the pipeline, our initial the input to our system is a bunch of articles, papers, book chapters that are dumped into our data lake, and these are not really structured. They are basically the document ID and the text, and they are in sequence files. Once there, we have a series of annotators that operate on that and produce little bits of output. This is not a true pipeline. This is more like little batches which run and stop. So each annotator reads something from the input and produces some annotations in an annotation repository. And annotators, which are downstream annotators, depend on the results of the previous annotators. So and finally, all these annotations sit in another annotation repository, and analytics toolkits can now come in and create insights out of these annotations. So we call our system SOTA. Basically stands for Solr Dictionary Annotator. It's built with open source components, Apache Solr, SolrTextTagger, OpenNLP, Spark for the client. We have borrowed ideas on fuzzy searching from open source libraries, fuzzy wuzzy being one of them. We have also contributed it back to open source. You can find it on GitHub at Elsevier Labs OS. And we have also put it in Spark packages. It's under applications or tools, whichever, either one will give you that. The architecture of the system by itself, it's really a web service written in Scala, and it fronts a Solr index. And there are two kinds of matching that we have. One is exact matching, case sensitive and insensitive, and the other is fuzzy. So for the exact matching, we are using SolrTextTagger, and for the fuzzy matching, we are using OpenNLP. Our client sits in a Databricks notebooks, but it could actually sit anywhere if you wanted. But because our entire pipeline is on Databricks notebooks, which is why we did this. So we read off our annotation repository, we extract the text, send it down to Solr, get back the annotations, write back the annotations back into the repository. That's our pipeline. There are advantages to having this kind of microservice. One advantage, obviously, is that I've basically cobbled together functionality from different systems available already. Starting from scratch would have been almost impossible or impractical at the very least. Obviously, there are disadvantages because of the loose coupling that we have. You have to kind of do things to make it work better in the sense that you have to get Spark to hit it hard enough and so forth. I'll come to that as I progress through the talk. A little bit of theory. So like I said, we have two modes of matching, two high-level modes of matching. The exact matching side uses the Hokorasek library, the Hokorasek algorithm. It treats the dictionary as an FST, a finite state transducer. It's basically a big graph data structure, a tree kind of thing, and streams the text against it. So all patterns are matched simultaneously in this sort of thing. If you look at the diagram below, it's for a very small vocabulary of his, he, her, hers, she, right? That you can find these words if you traverse the tree. However, for large dictionaries, it's still not possible to have this in memory. So the breakthrough comes across when Michael McCandless, Lucine's Solr committer, he implemented FSTs within Lucene. He basically used the fact that Lucene stores all its terms in a sorted order, and he created this FST, which makes it much more memory, compact in terms of memory. David Smiley, he built SolrTextTagger as a Solr plugin to handle a very, very similar problem to what I'm handling now. And I basically used SolrTextTagger to do the exact case matching. The fuzzy side is a little different. I take each dictionary entry and pre-normalize it to various different forms. So if you look at, this is an entry from Mesh. And so I have the original version, the lowercase version, which is basically just lowercase. Punctuation, which is the punctuation removed. Sorted, where the words are all sorted in a little string. And then stemmed, where the sorted string is now each word is stemmed, right? OpenNLP is used to parse our input text because we are getting documents in. So we parse it into phrases, and then we normalize and depending on what the user has asked for, what normalization level, we parse each, we normalize each phrase down to that particular level, and then we match it against the dictionary. Okay, so this was about the theory, and a little bit about the features. So we built it, I kind of got the inspiration from Elasticsearch, where everything is a JSON object, and so it's just like that. You create a request as a JSON object, send it over HTTP post. The server responds back with another JSON object, which you parse, right, to get your results. So obviously, this makes it language agnostic and cross-platform. We have used initially Python notebooks and then Scala notebooks on Databricks. But you could actually use it from standalone clients, Spark jobs, whatever. Anything that can do HTTP and read and write JSON. The services the system offers is basically index.json, which is basically a health check, I'm alive kind of thing. The single lexicon services, the annote.json and the matchphrase.json, both of them are for annotation. The first one is for annotating text, and the second one is for annotating phrases. So the second one came up because we were doing annotating triples, where we didn't actually need OpenNLP to chunk the data. So we could save some time. Multi-lexicon services, we have two of them. One is dix.json, which lists all the lexicons available, and the coverage.json, which allows you to send in a text and matches against all the dictionaries possible and gives you a kind of a coverage. So it tells you, essentially you would use it to figure out which dictionary you want to use, right, for your system. The indexing services, delete.json, add.json, initially they were, backend services. They were not exposed. But because we wanted everything to be self-service and, we put them out. There is obviously, if you delete.json, you can knock out the entire, dictionary. However, we have a small group who are using it, and they know what they're doing. So if they knock it out, they create it again. Add.json, you add it back, right? Add entries into the specific. I'll actually cover the annotation service and the loading part. Other services are kind of ancillary, so, but these are the most interesting and useful ones, I think. So the annotation request, in this case, we are trying to match author affiliation strings against a list of countries. We're trying to get countries out of the authors, of the authors of the, the countries from which the authors came for a particular document. So the affiliation string here is an Institute of Clean Coal Technology, East China University, where our lexicon is something called countries, which has about 294 entries, and with an ID and a bunch of names for a country. For instance, United States, right? US, USA, right? That sort of thing. United States of America. And the system would respond with a sequence of 0 or more annotations, if it finds any. The annotation has an ID. We are using URIs, but you can actually use anything that works for you, as long as it's unique. The covered text tells you what text matched, and the begin and end are the begin and end character offsets. Confidence is a number between 0 and 1. 0 is really bad, 1 is really good. Our original client was written in Python because our NLP team was basically mostly Python people. But then we moved to Scala for speed. But while we were in Python, we were using JSON and the request libraries, and we really like them. They make your code like really short and readable. So when the time came for us to move to Scala, we basically created functions that would hide that kind of all the gory details and make around. So here's a Python client to do an annotation. If you go down to the last 2 lines, the input is an RDD of the document ID and the document text. You pass it through annotate function here. And inside annotate, if you notice, is basically just creating a map with 3 keys, lexicon, text, and the matching type, expanding it out into a JSON document, taking the JSON document, posting it to the server, and getting it back, and parsing it back into a structure. The same thing in Scala, except that notice that instead of input.map, we are using input.map partitions. And this is because we want to create the HTTP client once for each partition. And so the Python did not allow us to do that, or at least the request library. But here we are, and in the inner iterator, we actually, the pattern is exactly the same. You build a map, make a JSON, send it, get back a JSON. Also, understanding the Spark is lazy, the count has to be there to just trigger the whole thing off. This is basically the results of that experiment that we did. It's not that interesting unless you have the context. The next part is loading the dictionaries. Our dictionaries, the format that we care about has basically 3 things. The lexicon name for each entry, the entry ID, once more, it has to be unique across lexicons, and a list of possible synonym terms. The idea of having multiple synonyms is basically to increase findability, right? So in this case, for instance, if you look down, this is an entry from Mesh, where baby tooth, dentition's primary, milk tooth are all synonyms of the same thing, right? And if any of them match in the text, then our system, Solr, returns this URI, which is M002, whatever, right? Also, one more thing to note is that because we are dealing with a data store, we need to commit. And for performance, it's better not to commit after every record, right? So here's the Scala client for that. As before, it does a map partitions and instantiates a Solr client for each partition. The way in which I have done the commit is I took the inner iterator, I zipped it with an index, and then I'm doing a mod hash mod every 100 rows to turn the commit on. So, it does 99, the 100th row it turns commit, moves on. And finally, I do another commit from the driver to take care of any stragglers, right? This is because this is how I knew how to do it then, right? Since then, there are other things, other ways you can do it I've figured out or I've learned. One of them is to actually move it into Solr, where you can do auto commit every 500 or every 1,000 or whatever. There's another way here where you can actually look at the has next element of the iterator itself and figure out the last element, right? And the last element, you hit a commit. So that's another way to do it. Next part of it is like, we wanted to scale out, right? So once we built the system and built a much more truncated version of this system, the question came up is, is it useful, right? So kind of one of the things that were thrown out, the Science Direct corpus of 14 million documents was what we had, in mind at that time. So the idea was, we should be able to annotate this corpus in a reasonable time. Now the question is, we did not actually have an idea of what reasonable was, but we had an idea of what reasonable wasn't, right? So 1 year, not reasonable, definitely, right? 1 month, probably not reasonable. 1 week, now we are talking, right? Somewhere in that ballpark. So that was what we started off with. So we took about 10K records, a sample out of the 14K, and started testing with it. And our first test showed an average of 3 seconds per document. And this was within our 3 large box, 15 gigs RAM, and 2 CPUs. And if you multiply that out, it works out to 16.2 months, so definitely not going to work, right? So 2 questions arose at that point, is, could we make the process faster? Or if we could not, or in addition to, could we also scale out? So, over time, so the first thing we did was we tried to find out where the time was being spent. So this is like a 3-layer cake. Spark calls Soda, calls Solr, right? So we instrumented at each layer, and we plotted the chart. And as you can see, the majority of the time is spent in Solr. There is some time which is spent in Soda, and as the transactions get shorter, it becomes more marked. And Spark has almost no overhead in this case. So the first thing we did was, the reason why we figured that the reason why Soda had this fixed overhead was because it was doing too much HTTP. It is reading HTTP, then serializing and deserializing. So if there was a way to cut that down, right? So one thing we noticed from our annotation repository, what we were getting was a sequence of paragraphs, right? Each paragraph being a sequence of text. And on average, there is about 40 paragraphs per document. It varies, but it's 40 paragraphs in general. So essentially, for each document, we're making 80 HTTP calls back and forth. So one obvious thing that we did was we took all of them, we put them all together in one big major document, and we put space padding so the offsets remain okay, right? And then from there, we got actually very good results. So our time, the mean time for annotating one article dropped from 3 seconds to about 1.4 seconds. So approximately a 2 times improvement. If you look at the medians, it's actually a 7 times improvement. If you look at the chart, the blue ones represent the after picture, where we created our mega document. And you notice it's taller and skinnier, saying that most of the elapsed times, most of the documents were done faster than in the previous set. The second big optimization we did was to tune the GC on the Solr side. Out of the box, Solr is, it would GC really frequently, go into full GC, and then that would slow down Spark and cause the job to fail. Didn't happen all the time, but happened enough that it became really, really annoying, right? Our current index size is just 2.1 gig. We ultimately ended up doing some changes, tuning, based on internal and external guidelines. And we ended up with a heap size of about 8 gigs. And we also upgraded to the next big size of machine, to 30.5 gigs. The diagram here, the top diagram, shows the memory utilization. The red part is the memory used, and the green part is the total JVM size. And if you notice, and this was taken over 2 days of Solr continuously being hit in annotations. So we ran the job for 2 days, and then we picked up the GC logs. And if you notice that it's oscillating around the 3 gigabyte mark, right? And the actual GC pauses are varying between 0.06 and 0.12. And over this entire 2-day period, I took a heap dump and checked, and there was like 0 full GCs. So this is like a really nice picture. I mean, it's made me very happy. The third optimization we found was that we are not, so we were not loading Solr enough, right? So typically Solr is a kind of an OLTP thing which is meant to be hit, with a lot of short processes, short hits, requests. However, our initial cluster that we were working on from the Spark cluster was 1 master plus 2 workers. Each worker had 4 cores. So we were on the Solr side, we noticed that almost throughout the session, it would be pegged at 8 requests, right? Exactly equal to the number of cores. So, and there was, it seemed to be underutilized. If you look at top, it was like really low numbers. And so what we did was we increased the size of the cluster to double that. So master plus 4 workers gives us like 16 cores. And then we ran some experiments on that. That actually made it much better. And so we varied the number of partitions, and we noticed that when the number of partitions on your input is about double the number of your cores, you get the best kind of results, right? You can see in the graph the actual throughput being measured. And it was approximately about 5 documents per second with number of 30 partitions. And that actually translates to a little over a month, like 32 days. So we were closer, but still not in business. We then decided to scale out Solr. Actually, we had scaled out Solr already to fix the GC problems, right? We went from an R3 large to an R3 X large. And when we did that, our throughput increased from 5 documents per second to about 8 documents per second, which now brought it down to about 20 days, right? So getting closer. We then decided to upgrade, horizontally this time, scale out horizontally. And we put, so we basically cloned the Solr server, the entire thing. We cloned it into 2, put a HA proxy load balancer in front of it. But funny story, I mean, what happened was that that availability zone did not have 2 R3 X larges to give us. So we actually moved to 2 R3 2X larges. So essentially my capacity doubled, quadrupled, right? It became 4 times. But that also gave me a chance to work with, increase the number of clusters and see what happened, right? So then I took the same 1 master plus 4 workers, and then I noticed that my throughput just went up in the bigger machine from 7.9 docs per second to about 8.62 docs per second. For considering that I just quadrupled my capacity, it didn't seem like much, right? So I looked through the network logs and figured, noticed that I wasn't stuffing the pipe enough, right? So I needed to put more stuff in the pipe. So the only way to do that was to basically increase the number of workers by, so ultimately I stopped at 1 master plus 16 workers. And that gave me like 26.845 documents per second, which translates to about 6 days for 14 million documents. So this is where I stopped. And I also plotted the throughput against the number of workers, and you'll notice it's like linear, right? So I can actually, scale out linearly to any, I can get even faster if I wanted to. So we actually haven't done the 14 million. What happened was that the system proved to be pretty useful. And so we have been doing other things that are more urgent. So, it's been running for about a month, and that's how it is. But what it gave us was the ability to actually predict capacity, right? So here's a thought experiment. So example, if you wanted to annotate these 14 million documents, say, in 3 days, right? The throughput that you would require given the kind of, the requirement is 54 docs per second, approximately double what we have right now. The number of workers based on 54 docs per second is 36 workers, given 1.5 docs per second per worker, right? And this is okay. This is kind of for our system. So this is not, 1.5 is basically local to our system. So from that, you can figure out what is the number of simultaneous requests you're going to hit Solr with, right? Because you have 4 cores per worker, so you have 36 workers, so 144 simultaneous requests. And given that each Solr server can take a sustained, has a sustained capacity of about 30 to 35 requests that can handle, comfortably, you would need 5 Solr servers, behind an HA proxy thing. So this was where we stopped, and we do have some plans. We want to add more dictionaries in our system. We have 6 already. We are keeping on growing on that point. We want to investigate lexicon-centric scale-out, although this is not, it's not as popular as the next one, where we want to basically move to Lucene and eliminate the HTTP overhead altogether. So that would involve writing to a message broker and then having Lucene, clones just reading off it. And that's pretty much what I have. So I'm open for questions. If you guys liked it, please go ahead and download, the software. If you have changes, requests, updates, pull requests, happy to take them. So, questions?
So thanks for the talk. I was just curious. Did you measure the network usage and going from there? Do you think that we will meet network capacity at some point, so not to be able to scale linearly at some point because you make too much traffic between the workers and your SODA service?
Okay, sorry. Did I measure network capacity?
Yeah, because I mean,
okay.
maybe for linear scalability at some point you will meet network limits.
Yeah, I actually didn't. The whole thing that we were doing here is based on AWS, pieces. So it's within the AWS network. I don't know what the network bandwidth is between machines. I just connect things up together.
We have time for one more question. Okay, let's give Sujit a big hand.
Thank you, guys.